Welcome to this lecture on mathematical finance. Today, we are going to explore a fascinating and highly practical concept known as the forward rate. Imagine you are planning a major purchase next year, like a car, and you know you will need a loan. But what if interest rates skyrocket by then? How can you protect yourself today against the uncertainty of tomorrow? This is exactly the problem the forward rate solves. Let us dive in and see how it works. Now that we understand the basic motivation, let us define what a forward rate actually is. In simple terms, it is an interest rate that you agree upon today for a loan or investment that will not actually begin until some specific date in the future. This allows people and large companies to plan ahead without worrying about unpredictable changes in the economy. In mathematical finance, this forward rate is not just a guess. It is the exact future interest rate implied by the current zero rates, which are also known as spot rates for different maturities. A zero rate is simply the rate earned on an investment that pays no intermediate interest, starting today and ending at a specific future date. Building on the idea of zero rates, we must introduce a core concept in finance called the no arbitrage principle. Why does this matter? Because financial markets do not allow for free money. The forward rate mathematically connects two different zero rates to prevent any risk-free profit opportunities. Think of it this way. If you invest your money for 2 years, you should end up with the exact same amount of wealth as if you invested for 1 year and then reinvested that money for the second year at the forward rate. Put another way, the forward rate is the break-even future interest rate that makes a short-term and a long-term investment strategy perfectly equal. This principle of equal returns leads us directly to the mathematical formula for the forward rate, assuming continuous compounding. Conceptually, this formula finds the difference in total accumulated interest between the two periods and divides it by the length of the time gap. Let us look at the symbols. RF is the forward rate we want to find. R1 and R2 are the known zero rates for the short and long periods, respectively. T1 and T2 are those time periods, measured in years. Notice the numerator. It subtracts the total interest of the short period from the long period. If the long-term rate R2 increases, the forward rate RF must also increase to make up the difference and maintain the balance. Before we move on to a concrete example, let us visualize this concept with a timeline diagram. Here you are seeing the two equivalent investment paths we just discussed. The horizontal axis represents time in years. The top path shows a single, long-term investment locked in at the rate R2 for the entire duration from time 0 to T2. The bottom path shows the equivalent two-step journey. First, you invest at the short-term zero rate R1 until time T1. Then you roll that money over at the forward rate RF until time T2. Because both paths start and end at the exact same points in time, they must generate the exact same financial return. Now that we have our formula and a clear picture of the timeline, let us see this with a concrete example. Suppose a bank offers a 1-year zero rate of 3% and a 2-year zero rate of 4%, both continuously compounded. We want to find the implied forward rate for the second year. First, we identify our given variables. The short time period T1 is 1 year with a rate R1 of 0.03. The long time period T2 is 2 years with a rate R2 of 0.04. We always start by writing down the general equation to prevent substitution errors. Then we carefully plug in our known values for the rates and the times. Continuing with our calculation, we perform the basic multiplication in the numerator first. The 2-year investment accumulates a total rate factor of 0.08. The 1-year investment accumulates a factor of 0.03. We subtract these values to isolate the interest belonging only to the second year and divide by the 1-year gap. This gives us a final calculated forward rate of 0.05 or 5% per annum. Physically, this means if you invest for 1 year at 3%, you must earn exactly 5% during the second year to match the overall return of a 2-year investment at 4%. The market expects interest rates to rise. Let us look at a slightly more complex scenario involving months instead of whole years. A financial analyst observes an 18-month zero rate of 5% and a 24-month zero rate of 5.8%. We need the forward rate for the 6-month period in between. The strategy remains exactly the same, but we must express all time periods in terms of years. So T1 is 1.5 years and T2 is 2.0 years. We write down our core forward rate equation again. This formula works perfectly for any time intervals as long as the time units match the annualized rate units. We then insert our specific decimal values into the equation. Moving forward with the arithmetic, we multiply the terms in the numerator. The 2-year total rate factor is 0.116 and the 1.5-year factor is 0.075. We subtract the smaller factor from the larger one to isolate the interest for that final 6-month window. The difference evaluates to 0.041. This number represents the raw interest accumulated over just a half-year period. Notice that the denominator is 0.5, which represents the length of the forward period itself, exactly 6 months. To finish the calculation, we must divide our raw interest by 0.5 to scale it properly. Mathematically, dividing by a half is the exact same as multiplying by 2, which annualizes the rate for that 6-month period. The result is 0.082 or 8.2% per annum. This is a significant jump compared to the earlier periods. It tells the analyst that to justify the higher 5.8% rate over 2 years, the market must be pricing in a very high interest rate for that specific 6-month cap. Investors would demand this high rate to delay their returns. Now that we have successfully used this formula in multiple examples, let us understand exactly where it comes from. We are setting out to mathematically prove the forward rate formula using the no arbitrage principle. We start by equating the total growth factors of the two investment paths under continuous compounding. The left side is the growth of $1 invested for the long period. The right side is the growth for the short period multiplied by the growth during the forward period. Because both paths carry zero risk and cover the same time, they must be equal. To simplify, we take the natural logarithm of both sides. This cancels the exponential functions and brings the exponents down into a straightforward linear equation. Continuing from our linear equation, our goal is to isolate the unknown forward rate, RF. First, we subtract the short-term accumulated interest from both sides. This leaves the forward rate multiplied by the time gap on one side and the difference in total accumulated interest on the other. Finally, we divide both sides by the time gap, T2 minus T1. This gives us our final derived expression. We have successfully proven the standard formula for the forward rate under continuous compounding. You can now see that it is not just a random equation, but a direct mathematical consequence of ensuring no free arbitrage exists in the market. So, we have proven that the formula holds and seen how to calculate it. This brings us to why forward rates are absolutely critical in the real world of banking and corporate finance. They form the foundation for pricing forward rate agreements, which are contracts where two parties agreed today on an interest rate to be paid on a future date. Companies use these agreements to hedge against risk. For example, a business planning to build a factory next year can lock in their borrowing costs today, ensuring a sudden spike in interest rates will not bankrupt them. Furthermore, forward rates are the essential building blocks for valuing complex financial derivatives like interest rate swaps. We have covered a lot of ground today, so let us review the most important ideas. First, remember that a forward rate is an interest rate for a future time period that is mathematically implied by today's available zero rates. Second, it is calculated by finding the difference in total interest between a longer term and a shorter term investment. Third, this entire concept rests on the no arbitrage principle, ensuring no free profit can be made in the markets. By mastering these concepts, you now understand how financial professionals lock in future costs and safely navigate the uncertainties of tomorrow's economy. Excellent work today. You have successfully covered the full topic of forward rates.